privilege to introduce Fernando, though I feel it's really hardly necessary since he's been about rather a lot. He took his, but for those who don't know, he took his first degree in Buenos Aires. Then he moved to Ohio, where he was my friend Carl Rubin's first research student. Carl, I think, was in the process of proving one of the earlier cases of that at the time, so it was very nice for both of them. More recently, his basis has been in the University of Texas. This hasn't inhibited him from traveling practically everywhere else. His interests are a lot wider than elliptic curves. In fact, this week he's been chairing the workshop on number theory in physics, which is why I expect everyone knows him already. Now, I'm looking forward to listening to his talk, but I was instructed by Nick that before he started, I should say a minute or two about why we thought of the conjecture. Difficult to fit into 1 or 2 minutes, but I should start off with a warning that anything one tries to remember after 50 years is more likely to be what one thinks ought to have happened than what actually did happen. And I should also apologize to those who don't know quite a lot more about elliptic curves than Peter and I did when we started, because the few words I have to say are, well, they can't help being technical, and I haven't time to define anything at all. Now, back in the 1990s, 1950s, one of the hot subjects were Tamagawa numbers. If you've got a linear algebraic group G with an invariant differential omega, there's a magic, miraculous measure you can define. You integrate over the G defined over the Adel's. The Adel's are essentially the product over all completions, factored by the rational points of G, and then you integrate the invariant differential, and that makes sense. And it makes real sense, it's invariant under all the messing about you can think of. So you get this number, which is a rational number, and indeed it's miraculously 1 if the group G is simply connected and semi-simple. Now, this little formula is, I'm afraid, a horribly condensed piece of information. But it really tells you all about Siegel's local global theory of quadratic forms, which is extremely precise and beautiful. Now, it's natural to wonder whether you can get something similar for the other sort of algebraic group, abelian varieties. This is true for a linear algebraic group, but suppose you've got an abelian variety, and the only abelian varieties we knew about at the time were elliptic curves, and then you try to do the same thing. You integrate an invariant differential of the relevant space, and you think, now, what will this do? You thought let's look at that, or something like it, and try to make sense of it, and then use computers to see if anything was true. And I have to warn you that there's an absolutely immediate difficulty. That makes sense, that doesn't. Because this quotient has some sort of geometry or other which no one has yet succeeded in understanding. Understanding it might be a good way of getting on the right road to earning $1 million, but anyway, that didn't work. So we had to pull the formula to pieces, and I said what those ideas were. So pulling the formula to pieces, the integral over that's essentially the product over completions of the integral, those which are the p-adic rings and the reals, and this you can evaluate. This is a period times the product over places of CP NEP over P, just like Philip wrote yesterday, who went to the right workshop. Well, that's another point on the elliptic curve. Because we can evaluate those. And then what we were driven to do was compare that with the group of diagonal points and see if there's a correlation. And before I move on, I should make an important remark that this is formally simply what you get by taking the L function of the elliptic curve at s equals 1 and actually it's the inverse. And that's important because even then, 50 years ago, people knew that it was likely to be much more productive to look at the value of an L function at s equals 1 than look at some horrible infinite product which probably doesn't converge. So what we thought, I think right from the start, was that we ought to look at looking at that. It was a very long time ago, and we were very ignorant. And unfortunately, we couldn't do that initially because we didn't know any elliptic curves whose L function actually was an elliptic, actually was an analytic function. So though we could talk about that, there was a conjecture of Hasse saying that that was always an analytic function. There weren't any cases that we knew. There were cases known, but we didn't know at the time. So to start with, we looked at that product. Well, for practical reasons, we looked at that product up to around x, and we did a great deal of computation, and we found between we played the trombone to the peonies successfully, and it worked. There really was a very strong correlation between how this increased as x went up and what the rank of this elliptic curve was. And it was really pretty clear that rank of E to the Q is the same as order of vanishing of L at s equals 1. But of course, that wasn't very satisfactory because though we'd done the computations ourselves and we knew we'd got lots of lovely evidence we could stare at and we found it convincing, there wasn't much chance of convincing anyone else, remembering that this product, though when the rank's positive, it does actually tend to increase. It actually oscillates about in a disgusting manner. And in order to convince anyone else, we certainly wanted, even to convince ourselves, we needed something more precise. So, as André Bay is recorded as saying, we needed to learn some mathematics. Now, actually, 1960 was a wonderful time for learning mathematics. It was a sort of reawakening after the war still, and there was lots of beautiful mathematics, quite easy mathematics, which was either unknown or simply forgotten. So there was a lot of mathematics for us to learn. We didn't quite know which bits to pick up. So we, well, to cut a longish story short, it must have been, I think, the prompting of Ian Castles that we suddenly realized, there are Hacker L functions. So that if E has complex multiplication, so for instance, if it looks like that, then this L function is a nice analytic function which was analyzed by Hecker in the 1920s, and one could indeed examine its behavior near s equals 1. We could evaluate its value at s equals 1 perfectly easy. And again, to cut a long story short, everything worked, and over to Fernando.
Thanks very much for the invitation to speak, and thanks, Brian, for the introduction. So, the story about elliptic curves and the conjecture is about rational points on curves, in particular elliptic curves. So let's run quickly through what that means and what the context is. I'll try to give you some historical and mathematical context for this conjecture. So, probably a good place to start when talking about different equations that involve rational numbers is Diophantus, who wrote this book, Arithmetica, which is basically a collection of worked out problems that involve rational numbers. In fact, he only considered positive rational numbers. And this date is somewhat uncertain, but somewhat around 250 year. And then this was the book that Fermat used for his famous marginal comments in the edition of 1621. Here's a copy of the front page of that edition. So, to begin the story with elliptic curves, we mentioned Fibonacci, who was challenged. It's quite interesting to read the history, to me anyway, of how mathematics was done over the years. And at the time, challenges were very explicit. Somebody will write a letter saying, "Could you do this?" And then they will have to show if you could or not. So Fibonacci was challenged. This is in the 20s, and to do the following: Venitur quadratus something or other, which with a little help you will find that it means to find 3 rational squares that are the arithmetic progression with different spot. In mathematical terms, that means to find 3 rational numbers x, y, and z, such that the difference y squared minus x squared and z squared minus y squared is equal to 5. So one thing that we can do is manipulate this a little bit. Simple arithmetic defining u and v in this manner, you'll see that u squared plus v squared is y squared. And so if you scale the three numbers by 2, you find that 2uv is 5. The 5, that was the difference in the arithmetic progression. So you'll find that you have, on one hand, a triangle whose sides are rational to u, to v, to y, which has area 5. So these numbers got, Fibonacci called them congruent numbers, and are the focus throughout the talk. They'll come back as a very old problem that boils down to solving equations, solutions of elliptic curves in rational numbers. So Fibonacci wrote, in fact, a whole book, Liber Quadratorum, on the subject. And he claimed, for example, that the number 1 is not a congruent number. That is to say that you can't find a triangle, a right-angled triangle with rational sides whose area was 1. So the theme of rational triangles will also pervade the talk, because it's historically sort of a fixed point. It's a very, very ancient topic. As if you were in Gargo's talk yesterday, he showed us this Sumerian tablet which had examples of them. And so many of the problems of Diophantus and Fermat so were sort of played of things that had to do with right-angled triangles. So this is a very common theme throughout the history of the issue of rational points. Now, his proof was not adequate. In fact, it's actually a pretty difficult thing to do, to show that 1 is not a congruent number. And Fermat did it by a method he called the descent method. And this was, of course, much later. So, have you solved this challenge already? Remember, there was a x, y, z, the difference? No? Anybody? Okay, here's a solution. 31 over 12 squared, 41 over 12 squared, 49 over 12 squared, which is a sequence of 3 squares in arithmetic progression with difference 5. Okay, so Fermat, one of the pleasures of preparing this talk is that I read a lot about the history of this problem in rational points, and I found it extremely fascinating. Fermat in particular, I find a fantastic character, an incredibly interesting person that, of course, is very, very, very famous for his problem, the Fermat-Last theorem that Andy Wild solved, as we all know. But he had an incredible set of other things that really he did that were early on extremely powerful. And one of the things that is sad is to read his letters and how desperate he was to get someone to actually be interested in what he was doing. It's really kind of dramatic. I mean, he was sort of begging, and then he wrote to people like Wallace in UK, and he wrote to Huygens in the Netherlands, and they all kind of said, no, number theory, you couldn't care less. In some cases, absolutely, explicitly. And in particular, one point that seemed to have been a rankling point is that people didn't seem to care about negative propositions, like 1 is not a congruent number. That seemed to, Wallace was absolutely adamant that there was a complete waste of time. Anyway, so he challenged one of his many letters where he proposed things that obviously he knew how to do, and he just wanted to see others could too. So here's another challenge. So again, this theme of Pythagorean triples, that is to say, rational numbers which are sides of a right-angled triangle. But with the extra condition, and this is the kind of game that appear very, very frequently. Take the Pythagorean triple. How about one that has this and this other property? So, for example, I'll pick this one. You want a Pythagorean triple which has C as a square and A plus B as a square as well. Now, you do a little work, and you find that what he was asking can be formulated as follows. You want a solution in always rational numbers. X squared plus 1 equals u squared, and x squared minus 2x minus 1 equals to v squared. And there's a side condition of x equals to be less than minus 1, because if you actually want a triangle, you want the answer to be positive. So I'll come back to this type of equation. So Fermat eventually revealed what his solution was, and he claimed that he had the smallest solution, which is this. I don't know, I should have asked maybe if someone had found it first. So, is this surprising? Well, I think it is. Because you start with what looks like very simple equations which doesn't involve very large numbers, and gives an answer, and in fact, Fermat claimed it was the smallest answer, although it's a little dubious whether he actually has a proof of that, but it is indeed the smallest answer. And he did this by a method which at least Ray calls ascent, as opposed to descent, which is what I alluded to before. And this is a method which, in some algebraic simple manipulation of things, constructs a solution to a certain type of equation starting from previous ones. So you have some equation, some solution, and there's some procedure that is mostly just algebraic and produces another one. And this method is called ascent because when you do that, the size of the numbers tend to increase. So he obviously has something. You just don't stumble on this solution. But one of the things that is extremely irritating about Fermat is that he basically never explained what he did. There's very, very, very few things in where he sort of late in life sort of relented and kind of explained a few things. So let's then talk about elliptic curves. So this is the theme of the talk, the theme of the conjecture, of course. And these are also sort of the main actors in this whole story, because a lot of the problems of Diophantus, the problems that Fermat dealt with, were in what we would now call elliptic curves. So they can come in various flavors. This is the way that Fermat encountered them. So, for example, one example we already saw is an equation, two equations like this. So Diophantus called them double equations, or we call them double equations considered by Diophantus, which is two variables u and v squared equal to some quadratic polynomial with various constants. But a more common way that elliptic curves arise are equations of this form: y squared equals to a quartic, or even better, y squared equals to a cubic, or a variant of the double equation of something which has three terms. And Fermat, you have to apply his method in all these cases. Okay. So what does it all boil down to in modern terms? Which would be, if we continue with the historical line, would be anachronistic, because it's unlikely that Fermat would have expressed any of this in this form. But it amounts to the following. So E is an elliptic curve, an equation, for example, of the various kinds that I showed. If it has one rational solution, then this method of ascent that allows you to sort of manipulate solutions and produce others from given ones, in modern terms what it does is it tells us that the solutions in rational numbers of the equations have the structure of the abelian group. And you can, all of these various forms in which the elliptic curves arise ultimately can be boiled down to something of this form: y squared equals to a cubic. And in this form, the ascent method boils down to the following, which is something you're likely to have seen more than once. This is the graph of the curve, the real points of the curve. For example, I think this is y squared just x cubed minus 1 minus x. Then you draw a line. The line cuts the cubic typically in 3 points. Those 3 points add up to 0. But this, according to Ray, history of numbers, is very unlikely the way that Fermat would have thought of his method. he seemed not to be aware of this geometric interpretation of the ascent method. But that's how nowadays we think of it. It occurs mostly in that format, y squared is equal to a cubic. Now, so let's jump ahead and talk about what do we know about the problem of solutions of equations from rational numbers. Not just any equation, but one which geometrically is a curve, something of dimension 1. But already talking about using this geometric language is completely modern. But anyway, let's just set the stage to what is it that we actually know in general terms. So we have a curve, a certain genus. What can we say about the rational points? So it comes, this divides into what I'll call this rational trinity. There is the case of genus 0, the case of genus 1, and the case of genus bigger than 1. And very roughly speaking, this has to do with the degree of the equations. So it's a more sophisticated, the genus, a more sophisticated measure of the complexity, in a sense, of the curve. So in the case of genus 0, geometrically we will say that that is a projected line. If we look at its complex points, that's a sphere. And what do we know about the rational points? Well, this case is quite well understood. Either we have no rational solutions, and this is something we can find out, or if there are solutions, if there is at least one, then we can get all of them, and infinitely many, and they're given in a parametric form. And this is a very classical, well-known example. Again, the Pythagorean triples. This was known to Euclid, or who knows how further back. You can find the solutions to A, B, and C squares in this form by parameterizing the solutions with two other variables, U and V, in this manner. And just to illustrate how that you can prove, if this is our circle, which if you divide by C, you get A squared over C squared plus B squared over C squared equals to 1. That's a unit circle. If you have one solution, which we do know, the coordinates 1 and 0, then you draw any line, it will cut the circle at some other point, which has to be rational as well, and that gives you a point. And conversely, if you have a point, if I run this backwards, I'll get a line, and therefore I can get all rational points by describing the lines. The genus equals 1 case, which is the focus of the Birch Swinnerton-Dyer conjecture. Topologically, that's a torus, what we call nowadays an elliptic curve. Here's a torus. And what do we know there? Well, in a paper that Poincaré wrote in 1901, which I recommend very highly, he argued the following. So all the points can be obtained from a set of generators by ascent, by the process of operating the group. That is basically vacuous. We can take all points to be the generators. But in a way which I find absolutely amazing, he didn't even bother to say that what he thought was true, which is that the group was actually finally generated. It's not that he was conjecturing it. He just didn't seem to need to even think of the possibility that it wasn't the case. In fact, that is a theorem that was proved by Mordell, later extended by Bay in the 1920s. This group of points with this operation of ascent, of adding points together to form more or new ones, is a finally generated group, which means that it has the following form. It has a part T, which is finite, and a part that has infinite order, and there are sort of linearly independent copies of Z, and this number R is what we call the rank. T is finite, is what we call the torsion, or the torsion subgroup. And already Poincaré was well aware that this R was a fundamental invariant, a fundamental quantity associated to the elliptic curve. I'll come back to that. So what happens if the genus is bigger than 1? Well, we have a higher genus curve. So topologically, this is a sort of multi-fold donut. So for example, something with 2 holes, something with 3. And in this situation, the number of rational points is finite. This was conjectured by Mordell in 1922 and proved by Faltings in 1983. So that is the rational trichotomy. And so we see that at least there's one major question that remains open, which is how do we find this number R for elliptic curves? At least at a first level, we understand everything else about rational points on curves. And we can also briefly discuss the torsion. This is a much better understood. In particular, there's a very important theorem of Mason that showed that the size of this finite group T is actually at most 16. So there's basically all we wanted to know about the torsion is known. And so really the question that remains as the most basic one is how do we find what R is? And I saw an interview that they made on with Swinnerton-Dyer that you can find on YouTube. And he points out the following. The question, that is to say the question of what is the rank of an elliptic curve, was regarded, this is in the early 60s, as one to which there couldn't be a sensible answer. So there was nothing in terms of which to express this answer. So the question of course is a relevant one, but nobody could think of what could possibly be a way to give a sensible answer to it. Of course the rank has a definition. You want something that would allow you to figure out what it is in a way other than its definition. So already Poincaré recognized that this rank was a very important variant, and I would recommend very highly that you have a look at this paper because he must have had an amazing, so his mind must have been something unbelievable, and he just kind of leaps out of the page, and he just sort of grabs you by the neck. I mean, he's a powerful thinker, and of course it's interesting. I think if you asked people in the audience in different parts of mathematics what Poincaré did, it's very likely very few people will know that in fact he wrote a paper on rational points and curves. So he asked what, of course we can think of a basic obvious questions. What values does this rank take? How big does it get? Is it bounded? So there's the method of descent of Fermat, which I alluded to, but I won't explain, gives a procedure that will give you an upper bound for this rank R. But it does not guarantee that you will be able to prove what the rank is, even if you maybe think you know what it is. So one point I'd like to stress for now is that the group of rational points, or rather just the solutions to these equations, a given elliptic curve, is an infinite set if the rank is positive. So even just the question, is the solution set of this elliptic curve infinite or finite, is a very difficult one, and it can be formulated as a very simple question about the rank. Is it 0 or is it bigger than 0? So, again, back to Fermat. In 1657, he sent an explicit challenge to English mathematicians. Can you find a general rule to solve this equation in integers? And I'll use this equation to use as a parallel with elliptic curves. In fact, it was interesting back and forth with letters because he didn't seem to need to explain that x and y were supposed to be integers. So the first thing that the British mathematicians did is that this is trivial, and just told him not to solve it with rationals. And then he had to say, sorry, no, I actually meant integers, and so on. But indeed, they did come up with a a solution, sorry, I should have said D is a fixed positive integer, which is not a square, other than this thing is rather simple. So there's also an ascent method here. So let me explain it in this simple case how it looks like. So if we write solutions in this form, so x and y and u and v are solutions to the equation, we consider this quantity x plus root dy and u plus root dv, then I can multiply them, and if the first and alpha and beta were both solutions to the equation, then so is the product. And if I have a solution alpha, the conjugate or a change the sign root d will also be a solution, and the product would be 1. So this, again, the set of solutions forms a group. And the solutions actually can be found, and this is an Asian algorithm, which can be either expressed as in terms of continued fractions, or the Euclidean algorithm is essentially the same thing. And again, well, that is a little pedantic, but in parallel with the elliptic curve is an abelian group, which is finitely generated. But it's pedantic because the answer is actually fairly much simpler to explain. There's a torsion part, plus or minus 1, which always will be a solution, x equals plus or minus 1, and y equals to 0. And then every other solution is the power of a certain solution epsilon by means of this root operation. So epsilon x0 plus root dy0 is some, I chose it to be bigger than 1, is a fundamental unit. So this is a complete description of this. There is an algorithm fairly efficient to compute this epsilon, and so in a way this problem is more or less completely understood. Now I want to point out that there is also an analytic solution to this equation, which is as follows. You compute a certain product of the sine function. This is the sine that we learn in calculus. There's a chi, the exponents which are 0, 1, and minus 1 that I come back to, that depend on d. This is in fact a solution to the equation, as was pointed out by Gauss. So, by the way, the equation is called Pell's equation, although Pell seems to have very little to do with it. Seems to be a mistake of Euler that he got his name attached. So, if it is a solution, it's equal to epsilon to some power, some integer h. It turns out that this number h is actually something of interest to number theory as well, and in fact is something called the class number, which I won't say more about. But the point I want to make is that this I'll use as a parallel because it has all the features we wish elliptic curves have. An algorithm to find the generators, and possibly an analytic way to describe them, and a complete understanding of the rank, etc. So let me make somewhat of a sorry, one more slide before I get there. So the Pell's equation, so what are we, another way to interpret this, we simply want the integer points in a hyperbola. So for example, if d is 2, we want x squared, 2y squared equal to 1, and here we can find what the solution is, the fundamental unit, and just to show off, this is our fundamental unit, and of course we have the negative and the conjugates, and here's 1. So these this group, these solutions to the equation are sitting in this hyperbola further apart, because you get powers to go from one to the other. You take the power of this epsilon. Okay, so a small digression. If you look at this hyperbola, thinking of the real numbers, they all look pretty much the same. So what I like to point out that when you think of problems in arithmetic, there's sort of different realities that come into play. So I remember distinctly, if you allow me a personal note, when I started engineering, I did about a year and a half of engineering before I moved to mathematics. And I remember very distinctively when I first either was told or realized that R is an infinite dimensional vector space over G. I just thought that was absolutely mind-boggling. R is a line. How could it be infinite dimensional in any sense? But so if you think of the real numbers, you probably just think of the real numbers as a line. But if you're interested in rational numbers, then things look very different. So this reminded me of a short story, Death on the Compass by Borges. This is a detective story, a detective called Lombrot, that says to the bad guy Shylock right before the bad guy kills him. This is the very last paragraph of the story. He says, I know of one Greek labyrinth which is a single straight line. And now, of course, it's unlikely you find any other author that will have detective say that. But I always was struck by this line, because I think it's, in a mysterious way, very profound. So, what is it arithmetic then? And let's just look at I want to make one simple point. And so let me look at this. Simple statement. X squared plus y squared is a minus 1 doesn't have integer solutions. Now, before you start squirming in your seat, you don't even have to think about this. You know how to answer it. Well, there's no sum of squares to be negative. So now I give you this problem. X squared plus y squared equals to 1, 2, 3, 4, 5, and lots of 9s. Also doesn't have any integer solutions. And now probably this will take you a little longer to think. Okay? And the point of this is that the number ends in 99. So the beginning is irrelevant. So 99 is a number which is 3 mod 4. And no sum of two squares could be 3 mod 4. Because the squares mod 4 are either 1 or 0. So if you have two of them, you can now make 3. So that's just to illustrate the fact that when you're thinking about arithmetic, somehow this is a different reality. This is different things that go into understanding what's going on. Now, to illustrate this further, if I add 2 to the number that I had before, which if your business is dealing with real numbers, if you're constructing buildings or building bridges and so on, how could possibly that make a difference? But this one does have integer solutions. So there's something subtly different than what we used to when we consider things in an arithmetic sense. So again, back to the issue of sizes, when I talked about this challenge of Fermat that he gave a solution to, the numbers were big. So if we look at this Pell equation, it has one fundamental solution. What size does it have? Well, the thing that you discover is that the right scale to consider here is logarithmic. So what we should look at if we want to understand size of the solutions is not epsilon itself, but log epsilon. In fact, so log epsilon divided by root d oscillates very widely, but is never very big. So here's a plot of 2 log epsilon versus compared to root d for all d's up to 10 to the 5. Okay, so you see here, this is going to be a pretty big number. Right? This is logarithmic. So even without d being particularly huge, we have solutions that are very, very large. Not the right button. So let me continue with the Dirichlet the problem of the Pell's equation. So one of the things that we do in number theory, as Brian explained, is that you can what are the realities we have? We have the real numbers, but we also have all the prime numbers and all the periodic fields. So if we want to understand an arithmetic problem, we should look at it in all possible realities. So in a finite field, if we look at things modulo primes, the thing that we can do is count. And so if I let NP be the number of solutions to this equation mod P, then the ratio NP over P is 1 minus chi P over P, which is this number chi P that I described before, P chi P in this case being plus or minus 1, depending on how P and D are related. So the thing that we can do with this information is to put it together in a Dirichlet series, which is what Dirichlet did. And you can give that as an infinite product and expand it out as a sum. And what Dirichlet proved in 1939 is that the value of this Dirichlet series is exactly equal to this ratio that we were talking about. Okay, in particular, something that is non-trivial that follows from this is that this number is actually non-zero, because epsilon was the generator of this group, which is non-trivial. So with a little bit of analysis, you can see that another way to phrase the same statement, this is a bit subtle analytically, but you can see that this value of the L function at 1, if you recall what the L function looks like, if you look at this factor here, and you put s equals to 1, then it will exactly look like this ratio NP over P. So at least formally, this infinite product is exactly what you will get if you plug in s equals to 1 into this L function. And as I said, there's a little bit of a subtlety here analytically, because this infinite product, there's maybe some care to deal with, but you can show that this infinite product actually converges to the value of the L function of 1, which by Dirichlet's formula is equal to this quantity involving the logarithm of the fundamental unit. So this is in a way the model that the Birch and Dyer conjecture have for the case of elliptic curves. As I said, I'm trying to use this Pell equation as a parallel with what happens with elliptic curves. So, as Brian was saying, in the late 50s, Tamagawa numbers were up in the air. That's what they tell us. So, let me give you a very simple example of what this Tamagawa number in the air was. And it's a fantastic way to condense Siegel's formula, which is itself a elaboration of Dirichlet's class number formula. And it is about solving equations, quadratic equations in more variables than one. So moving in a different direction, keeping the degree, so to speak, low, but increasing the number of variables. So a very simple example would be to take the group gamma to be SL2Z. Okay, and this, for some number theorists, this is not a group at all. It's just the solutions to the equation AB minus BC equals 1 in integers. It's a quadratic form in 4 variables. So we can do the same thing we did, count the number of solutions mod P, call the number NP. The natural thing would be to look at NP over P cubed, because now we have 3 degrees of freedom. And you take the product, in this case there's no convergence issues, and you find out that the answer is pi square over 6. Or rather, if you're later, you find out that the answer is pi square over 6. And the reason is because that's nothing else than the well-known identity that the sum of 1 over n squared is equal to pi squared over 6. If you unravel this infinite product, you'll precisely find the sum on the left-hand side. So the way that this was understood was that you bring this thing, or maybe I'll do it
the other way, you bring this thing to this side, and you say, okay, what we have is a product over all primes, and also something that has to do with the real numbers, and the product is 1. And so when Brian mentioned that certain simply connected and simple semicircle groups have Tamagawa number 1, this is an example of this, and this quantity then arises as the volume of the corresponding fundamental domain of the action of the real points, of the integer points over the real points. So this kind of thing is a very simple example of what's up in the air. And now, I love that Brian said it was natural too. Now, I think you have to be Birch and Swinnerton-Dyer to think that was natural too. You could ask, well, what happens if we do the same with elliptic curves? So you do the same thing. I'll avoid these problematic primes where things are slightly different. Just the rough idea: we have an elliptic curve over Q. For most primes, we can make sense of it over a finite field Fp. We can count the number of points, the solution is mod P, and we can consider the product NP and P. And as Brian explained, this product doesn't converge, as it did in the case of SO2Z, but we can still look at the product after a certain x and compare and see how that behaves with x. And what you get is you write on the notes, strike gold. Because what happens is that this product numerically seems to behave in the following way. It seems to grow at a rate, at a rate that is correlated precisely with the rank R of the elliptic curve. I think that's just amazing. So, with the help, I believe, with Davenport and Castles, this was reformulated as something about the L function itself. And I'll just consider, we'll already talk about part 1, so to speak, which is something to do with the rank and not about that constant C that we see here, which has itself a lot of meaning. But the statement is that infinite product growing the way we indicated precisely matches the following statement, that the L function, which is built out of those numbers and P in a similar way that we built this series for the Dirichlet L function, has a 0 at s equals to 1 of order exactly R. Okay, and at the time, this was a completely meaningless statement because the L function was not known to even make sense at s equals to 1 for most elliptic curves. We know now, thanks to Wendell Wiles, that in fact it does make sense at s equals to 1. So that's a start. So let's go back to congruent numbers of Fibonacci. So a little bit of monkeying around will show that if you have a number n, it will be a congruent number if and only if the elliptic curve En it has infinitely many rational points where En is this curve. Okay, so by the Birch Swinnerton-Dyer conjecture, we now have at least a way to handle this question and decide whether this curve or any other has infinitely many points or not. We just should look at that infinite product and see whether it grows or it doesn't. Or if you look at the L function, you want to decide whether the L function vanishes or not. Of course, you may be thinking, how do you decide if a number is 0 or not? Which is a fair question. You can't prove that a number is 0 in your computer unless you know something about it in advance, like it's 0. But anyway, those are more subtle questions that I'll address. So let's, again, to compare, let's consider the situation of elliptic curves with rank 1. So we use the logarithm to measure, that was the scale to use in the case of the Pell equation. Logarithm of epsilon, that was the natural, logarithm of a unit, that was the natural measure to use. So in elliptic curves, there's also a similar thing, which is also logarithmic, but is called canonical height. It's a way to measure the size, in the right scale of the point. And this scale is again logarithmic. So if p is a point, y squared equals to a cubic, x and y of the form a over c and b over c in lowest terms. The height is, roughly speaking, the logarithm of the maximum of the absolute value of a and c. So roughly speaking, it tells us how big these solutions are, but again, it's sort of in a logarithmic sense. So here's a corresponding graph of all the rank 1 elliptic curves of conductor 10 to the 5. So the conductor is a specific quantity that measures, is analogous to the d that we had in the Pell equation. And this comes from John Cremona's table, so one of the things I'd like to point out is that by now we have extremely good both tables and computational abilities to deal with elliptic curves. And again, this is logarithmic. So if you look at this point here, that's going to be a very large solution. And this is a generator, so that's the smallest there is. Okay? So let's examine this a little closer. The elliptic curve happens to be this one, which has pretty size coefficients. It's a little more elaborate form than I mentioned, but essentially equivalent to y squared equals to a cubic. Now the conductor happens to be rather small for the size of these numbers. And if we look at the the generator of this rank 1 elliptic curve, the solutions are these. Okay? So this again should be surprising. Probably less so now, because we've seen already this phenomenon that things seem to have a logarithmic scale. So the log of the max of the A and the C is 171, and A in fact has 75 digits. So you're not going to find this point lying on the street. So is there something we could do to produce points on elliptic curves? It is, of course, one of the things that one quickly learns is that finding rational points on anything is hard. It's very hard. But there is, in fact, something analogous to the construction that I mentioned of Gauss with the sine function. And this was something that was discovered by Kurt Hertner in the 50s. And he uses the following fact. And it will be very quick summary. So any modular function has at Cm points values that are algebraic. And rather than explain each one of those terms, let me give you an example. So consider this Dedekind eta function, which is hopefully fairly familiar to most of you. So it's a function in the upper half plane that behaves under the SF2Z action in a particular way. And it was shown, for example, by Abel in 1828 that if you take the ratio eta squared of root minus 5 over 2 over this other eta squared ratio, you get this algebraic number, which, by the way, happens to be a unit, and which is even a stronger statement than just being algebraic, and it gives rise to these elliptic units, which are the analog to these solutions that we had of the Pell equation with the sine function. So here the sine function gets replaced by this more sophisticated modular function, and we have to evaluate it at special points, like the sine function has to be evaluated at also special points to get something visibly algebraic. So the point of this is that if you have two modular functions, they satisfy an algebraic equation. There's an equation that relates them. So this gives rise to a curve, and which is now called the modular curve. And if we evaluate these modular functions on algebraic points, on CM points, then we get algebraic coordinates of that curve that satisfy the equation. So amazingly, Heegner proved, using these ideas, that every prime number congruent to 5 or 7 or 8 is in fact a congruent number. So to do that, he actually used this idea of evaluating modular functions to produce points, algebraic points on some curve that were then transported to the corresponding elliptic curve and gave a non-trivial rational solution for the curve EP, y squared equals x cubed minus p squared x. And with that, he could show, therefore, that the prime p is a congruent number. This is an amazing achievement. Heegner famously also proved in the same paper Gauss's problem of class number 1 problem, but somehow the proof was not considered to be complete, and it's a long other story. So what happened after that, it was a development that in which Brian was very much involved. It was picked up that this was a very important construction, the idea of Heegner of using modular functions to create points. It appeared to be the case that the points that you get from this method of Heegner seem to be related to the derivative of the L function at 1. And this was eventually proved by Gross and Sadlier. And one form of the result is the following. If the L function at 1 vanishes, then there exists a Heegner point, one constructed by the method of Heegner, for which the derivative at 1 actually is related to the height of the Heegner point. So this is very much like what I mentioned before about the unit constructed by Gauss. You have some analytic construction of a point which happens to be equal to some particular multiple of a generator. So this is an amazing development that happened in 1986. And in particular, this statement, if we read it, we can read it this way: if the L function is not, L prime is not 0, then this point has non-zero height, which in fact means that it cannot be a torsion point, and so it actually is a non-trivial generator in the elliptic curve. So that means that the rank is at least 1. And that's the kind of thing that precisely the Birch Swinnerton-Dyer conjecture says. So there's been some other work surrounding these ideas, called by Rubin, Skinner. We can say, without getting into the very difficult details of exactly what is the statement, we can more or less say that the conjecture is known for rank less or equal to 1. So there have been also vast generalizations of the Gross-Sadlier construction, the Gross-Sadlier theorem by Delmon, Yuan, Shang, and others. Now, there's a bittersweet side to the story of Gross-Sadlier, which is that it turns out that it also shows that all of these points that you can construct by Heegner's methods, they're all multiples of each other. So, in the best scenario, what you will be constructing are points that happen to all lie in a rank 1 subgroup. So, it gives no way to pass this rank equals 1 barrier. And at the moment, we simply have no idea of how to construct solutions in a rank 2 situation. Now, what is the impact that the Birch Swinnerton-Dyer conjecture has had? Well, people have, for example, tried to understand the behavior of this rank, as Poincaré had asked. And LPs, I think, is the current record. They actually produce an elliptic curve that has rank at least 28. This is provably so. There's 28 different solutions which are independent, and there could be more, but it would be very hard to test, and there are. So, but the jury is still out on whether this rank could be bounded. One maybe can plot how the rank moved with time historically, but asymptote, and maybe Martha Manzo will explain to us that it goes down or goes up. I don't know. But is one of the things that Birch and Swinnerton-Dyer conjecture implies is that, given this example that it was found, its L function has to vanish to order 28 at s equals to 1. At least. That's just unbelievable. Now, to find the vanishing of an L function to any order higher than 3 is miraculous. Okay? In fact, one of the consequences of their theorem is that you can find elliptic curves that have a vanishing at s equals to 1 provably of order 3. And that, Goldfeld saw, has very important consequences for the calculation of class numbers. So I think it's not exaggeration to say that anything you prove about L functions will have repercussions somewhere else. These L functions are just an incredibly central object in number theory. So this connection between the class number problem and the Birch and Swinnerton-Dyer Brosagli was a real sort of bridge between the two subjects that Goldfeld found. And to finish, let me say some words about some recent results, some of which we heard from Angel yesterday's talk. So you can ask, well, maybe the rank is 28, maybe the number is bigger than that, but what can we say about things on average? So you can order your elliptic curves in some sensible way, try to understand how the rank is as the size of your collection grows. And Bhargava and Shankar managed to prove that the average rank of elliptic curves is in fact less than 0.89. It wasn't even known it was bounded before they came into the game. And Bhargava and Skinner actually proved that the average rank is positive, which again is a non-trivial statement. And you put all of these things together, and you can say that at least 20% of elliptic curves have true Birch and Swinnerton-Dyer conjecture. All of these curves have 0, 1, which is the bulk of the elliptic curve. Now, to prove that Elke's elliptic curve satisfies Birch and Swinnerton-Dyer conjecture is way, way out there. Another thing along these lines of Hegness and the congruent number problem is Ye Tian, who won the Ramanujan Prize for this work. In particular, he extended Hegness' argument to show that, and you can find infinitely many congruent numbers that are the product of an arbitrary number of prime numbers. So Hegne had proved specific prime numbers were congruent. This was extended to arbitrary products, specific kinds of primes, of which there are infinitely many of them. So that is probably the latest result that we have on the problem of congruent numbers. And I really have no idea what my time is, so I don't know if I'm going to go too much over time, but I'll finish with my last slide. And I'll give you what was one of Fermat's favorite quotes, which I like to also tell you, which is that many will pass through and knowledge will be the greater. This is a phrase that appears in the cover of a book by Francis Bacon, and this is supposed to be the port of the Hercules. This is the ship going to a new world, and the idea is sort of people passing through, and the more the better. So thank you very much.